Hello and welcome to another installment of the geometry videos. This is section 6 and this is a section about right triangle right triangle similarity. And so what I want to do is take a look at this concept of a right triangle altitude, okay? So if you had this big right triangle here, triangle ABC, okay? And let's say that we drew in this altitude here, okay, this altitude. Okay, which is another way for us to say height. But the unique thing about the altitude is that it creates a right angle with the base length of that triangle. Okay, so if we draw in that altitude, what that does is we then get two smaller triangles. So I get this triangle here. All right, I'm going to call this one, I got this small triangle here. And then I have another small triangle here. All right, so you need to see that you have three triangles. When you take one triangle and you draw a line down it, it separates it into two smaller triangles and then a big triangle, okay? So here are your smaller triangles here, okay? And then, so that's the smallest of the two, and then this is the second largest. And then if we were to like reorientate these, okay, then what we end up getting is we get three similar triangles, okay? This is the largest one, this is the second largest, and this is the third, this is the biggest, middle, small, okay? And what I know is that if I were to take, say, triangle ABC, okay, I could then make this statement here and say that triangle ABC, okay, is similar, so ABC would be similar to triangle DBA, okay? So is similar to triangle DBA. All right, I also know that triangle ABC is similar to triangle DAC. Okay, so then let's do this. Let's write that triangle ABC, the big triangle, is similar to the little one, triangle DAC. Okay, and then we know that these two smaller triangles are similar. So we can then say that triangle DBA is similar to triangle DAC. Okay, DAC. All right, so if you draw an altitude in there, so if you have a right triangle and you draw an altitude into that other triangle, it separates it into three similar triangles, okay? So now let's quickly talk about the geometric mean. And the geometric mean of two positive numbers, A and C, is the the geometric mean of two positive numbers, A and B, is the positive number x that satisfies this proportion here, okay? So the proportion that we can write here is that if I were to take segment AD, okay, take segment AD here, and then I'm going to draw another segment for DB, okay, we can relate those two sides, okay, and that's the hypotenuse of my big triangle here, to the leg of one of the smaller side, okay? And what I can say is this. I'm going to call length AC, I'm going to call this length X, okay? And then I'm going to call length AD, okay, I'm going to call that A, and then I'm going to call DB, I'm going to call that length B. Okay, so what we can then say is that, in order to fit this proportion here, I could take segment AD, all right, divide it by segment AC, okay, and then I would get segment AC divided by segment DB, okay, and this is the geometric mean, okay. Okay, and we could look at this another way. We could say that segment AD, okay, let me kind of go over these again. Let me go over this in purple. If I were to say segment AD, okay, here in purple, and then segment CD, and let's use green, okay, CD, and then BD. Let me do that over here. Okay. And what we can find out from here is that it works the same way. We can write the same proportion. And what I can do is I can say that the segment AD, okay, if I divide that by segment CD, okay, then I get that CD is then divided by segment BD, okay. And it kind of follows a similar thing, but this is really, notice how CD is your altitude, okay? And that kind of leads us into the next thing about the geometric mean and the altitude theorem, okay? And what that allows us to say is that the length of the altitude of the hypotenuse, the length of the altitude of the hypotenuse of a right triangle is the geometric mean between the lengths of the segments of the hypotenuse, okay? Doesn't make too much sense at this point. But what I know is this, is that if I were to come through here and kind of draw in, you know, what this stuff means, it means the length of the altitude of the hypotenuse of a right triangle, okay, which is this length here, the altitude, okay, and then the lengths of the segments of the hypotenuse, between the segments of the hypotenuse, okay, these values here correspond to here and here, okay? So then if we were to follow this idea, these segments come from the hypotenuse of the big side that's been changed, okay? So I can come in here and I can say that if I take x divided by the altitude h, then that's equal to h divided by y, the other side of that hypotenuse, okay? And this proportion will always hold true given a right triangle with this type of relationship given the altitude, okay? Now, the other thing that I want you guys to see here is that, you know, even though I have, you know, this length x divided by h and then h divided by y, we can flip this around, okay? We could rewrite this and say if I were to take the length of y, okay, and divide it by h, then that would be equivalent to me taking h and dividing it by x, okay? Doesn't matter which one you do, as long as, you know, h is on, you know, as long as you flip-flop h, doesn't really matter. Okay, so you can do it whichever way you want, all right? So let's do a practice problem here, and let's find the value of p in this problem by using the geometric mean altitude theorem, okay? So what I have here is the hypotenuse of my big triangle, okay? So I'm going to come in here and I'm going to draw in those separate lengths for that hypotenuse, and then I'm going to highlight the altitude of my triangle, okay? And so what I'm going to do is I'm going to take segment 1, which I'll just take 6, and divide it by the altitude, which is 15, and set that equal to the altitude, which is 15, divided by the other length over here, which is p, okay? Now, when you're solving this, you know, you could cross-multiply and divide here, you know, which is fine. Let's go ahead and just do that. I'm going to cross multiply and set up an equation. I'm going to do 15 times 15 is equal to 6 times p. So I've got 15 times 15 is equal to 6 times p. So 15 times 15, I believe, is 225. So 225 is equal to 6p, okay? And if I divide everything by 6 and by 6, then that's going to give me 37.5. Okay, so I know that p in this scenario is equal to 37.5. Okay, So it's your ability to recognize, what this figure looks like and then know what theorem to use. Okay, the next theorem is kind of interesting. This one is the geometric mean leg theorem, okay? And what that means is that the altitude of the hypotenuse of a right triangle intersects it so that the length of each leg of the geometric mean between the length of its adjacent segment of the hypotenuse and the length of the entire hypotenuse, okay? So we have this concept here, all right? So let's just take a look and see what this says. What this says is that if I take the length x plus y, which is the hypotenuse of my big triangle, so I'm going to do x plus y, and then if I look at the length of A is the longer side of the longer leg that I have, okay? So I'm going to highlight that in blue, okay? And then that's equal to me saying this, and then if you look at this, the larger, of the two right triangles here, then this is the hypotenuse of the larger triangle divided by the longer leg, okay? And that's where that comes in, okay? So then, all right, so I'm going to highlight this in red. Okay, let me make that a little bit smaller. So I'm going to highlight this in red, okay, over what's in blue, which is A, okay, and then I'm going to show Y also in orange here, down here, okay. Now we could do the same thing, okay, with the smaller triangle, okay. We could relate the hypotenuse of this length to the smaller triangle, all right. So watch what I do. I'm going to do x plus y, okay, that's in red, okay, that's here, okay, and I'm going to divide that by b, okay, and b is the smaller length of my whole right triangle, okay. Then if I take the and b is the hypotenuse of the smaller triangle, okay, and then if I take b, all right, so here's b, and relate that to x, which is the smaller length of that triangle, okay, and that's what goes down here. So I'm trying to color coordinate it for you so you can see, all right. So let's try this. Let's try applying the geometric mean leg theorem to solve for the value of E here, okay? So what I want to do is, when I think of this, all right, this is relating to the big triangle, okay? Okay, the hypotenuse of my big triangle divided by the leg that I'm looking for, okay? And then I want to take that same leg, okay, which is the hypotenuse of that, and divide it by the adjacent segment of the hypotenuse, which we'll do 4, okay? So this is for the small triangle, okay, the small triangle, okay? So watch how I go through this, all right? So I'm going to do the hypotenuse here, so that's the length of ED. So I'm going to do that whole length, which is ED, which is the length of 20. So I'm going to do 20 divided by the length E, okay? So let me do this first. Take the hypotenuse, okay? Divide it by my length, which is E. Okay, so we'll call this length E. All right, so I'm going to put that here. All right, I'm going to divide that by E. And let me do E like that. Hold on. Let me do it like this. E, okay? And that's going to be equal to that same leg, E, okay, that leg E, and then divided by the adjacent leg. So now here's what you have to figure out, okay? I had the big triangle, okay? This is my hypotenuse. This is my smaller leg. Now, when I look at the small triangle, here's my hypotenuse, here's my smaller leg. Okay, so we have to realize that this is the small leg of the big triangle, and this is the small leg of the small triangle, so this number down here is going to be 4, okay? And that's the adjacent segment of the hypotenuse. Okay, now if we go through this, all right, and we solve this for E, let me just do this over here so we got some room. Okay, I've got 20 over E is equal to E over 4. Okay, cross multiply, and so I'm going to get 80 is equal to E squared. Okay, take the square root of both sides, and we get that E is equal to the square root of 80. Well, 80 can be rewritten as the square root of 16 times the square root of 5. Okay, 16 times 5 gives me 80. Keep them under the square roots. All right, and then I want to take the square root of 16, which is just going to give me 4. Can't take the square root of 5, so that's that. And so E is equal to 5 times the square root of, or 4 times the square root of 5. Okay. All right, so now let's talk about something that's extraordinarily important. And I want to talk about the fact that I have a friend. Okay, and my friend has a name of Pythagoras. Now, you will sit there in class and you will say, hey, Mr. Police, I don't know how to do this. Well, guess what? I have a friend, okay? And my friend is Pythagoras. Now, Pythagoras, the reason why he's my friend is because no matter what, this relationship will always work, okay? If I take this length A and this length B and I square them and I add them together, then it is equal to the third side squared. Now, Pythagoras is always there for you. Unlike someone I know, and I won't name them, although they are my boss and their name is Jim Smith, you know, if I ask Pythagoras, let's just put it this way. If I ask Jim to hang out on a Friday night, you know, let's say I ask Jim on a Tuesday to hang out on a Friday night. He's going to say, yeah, that's great, sounds good. And then, you know, Wednesday I'm going to say, hey, Jim, I'm really excited to hang out with you. You know, excited to grab a burger and watch a football game or something like that this weekend. And then Thursday I come by and I keep saying, hey, I'm really excited to see him. And then Friday, he's going to come up to me and he's going to say, sorry, dude, I can't hang out. So then who do you think I hang out with? Oh, yeah, you got it right. I hang out with Pythagoras. He's never going to disappoint you. He's never going to, you know, tell you that it's that he's going to hang out and then something suddenly came up. Okay, he's always going to be there for you. All right. So, you know, what we have, the theorem says that in a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. And you've probably seen this before, okay? Now, we're going to use this a lot. We're going to use it in the next unit quite a bit. It's really fun, and get used to it because I won't take no for an answer, all right? So we have all these different relationships here, and I just want to go through each of these triangles and kind of write the Pythagorean theorem for each. What I would say in this triangle here, okay, my legs in this one are these two, and then my hypotenuse is always the longest side, okay? So we would say here that if we took a squared plus b squared, that's equal to c squared, okay? Now, c can be rewritten as the quantity e plus f squared, okay? So you could say this, that a squared plus b squared is equal to the quantity e plus f squared, okay? That's one way of doing it. Down over here, okay, if I were to highlight my legs and the hypotenuse, okay, then I would get that h squared plus f squared is equal to a squared, okay? And then down here, same thing. If you wanted to set it up, here are your legs, okay? Here's your hypotenuse. You would then come over here and you would say e squared plus h squared is equal to b squared, okay? So if you just wanted to set those up. Now let's go down here and let's use the Pythagorean theorem to find the side lengths in a right triangle. Now what you have is you have this big triangle here with a right angle, okay? I also know that if this is a right angle here, then this is also a right angle, okay? So now what I want to do is show you that I have a right triangle here. I have two of them, okay? And I have three of these sides, okay? Or two of the sides, and I'm trying to find this side, okay? Now what I do is I'm going to call this length A, I'm going to call this B, and then over here I'm going to call this C. C is the hypotenuse, okay? So when I set this up, I'm going to say that I have, if I use the Pythagorean theorem, a squared plus b squared is equal to c squared, all right? If I wanted to plug in my value for a, that's going to be a value of 10. So I've got 10 squared plus b squared, which is x, okay? That's x squared. And then this is equal to c squared, which is 26 squared. Okay, so let's evaluate this and let's solve this. So what I'd want to do is I'd want to take 10 squared. 10 times 10 is 100, okay, plus x squared. And this is equal to 26 squared. So if I were to take 26 times 26, that's going to give me a value of 676, okay? And then I'm going to subtract 100 from this side, okay? And as a result, this is going to give me x squared is equal to 676 minus 100, which is going to be 576, okay? And then what I'd want to do is I'd want to take the square root of both sides, all right? So then that gives me a value of x that's equal to the square root of 576, which is a length of 24, okay? So this value for x is 24. Now this will pop up quite a bit, folks. Okay, on the SAT, on the ACT, you will be doing the Pythagorean theorem all the time. And now here's the cool thing. Now that I know that this length is 24, okay, notice how I have another right triangle here. And I could use the Pythagorean theorem to find the length of EF. Okay, it's not having us do that right now, but you could do it. So I hope you guys enjoyed this video. I know it's kind of a lot of information. It's kind of some brand new stuff for you. Maybe a little bit weird. But I hope you enjoyed it nonetheless. This is it for the Unit 5 videos, and we'll see ya in Unit 6.